with recording. All right, so let's get started. So we talked about this, the fermion system with the chemical potential mu, which is positive now. And then we found the ground state is given by basically all states with energies up to given by chemical potential called Fermi energy occupied, and all states above that energy vacant, unoccupied, and that is the ground state of the system. And so this is the situation we call the Fermi liquid. And we look at an example of the metal. And we also look at the example of the white dwarf, that's a star, supported by the Fermi degeneracy pressure against the gravitational collapse. And so that actually turned out to give you the mass of the sun in terms of the fundamental constants. That was actually a really remarkable thing to do. So that's what we talked about. So that's the ground state. So the next question, obviously, is what would be the excited state? And let me get this laser pointer for the annotation. I hope you can see this. All right, so the question next is the excited state. And obviously, just like in the case of the atoms you're familiar with from quantum mechanics class, the way to excite the system is grab one of the states that's already occupied and bring it over to one of the states that is not occupied. So one electron goes from a low energy state to high energy state. That's how you can excite the system. So you grab one, namely that you annihilate an electron in one of the states, and you create an electron in one of the unoccupied states. So this is the typo, I'm sorry. So this BP should act on 1 instead, I apologize. So occupied state 1 should be now removed with the annihilation operator and make it unoccupied. And then unoccupied state up here would create a particle. So now you have an electron up there. So you annihilate one here and create one there. And that's what you can create an excited state.
Professor?
Go ahead.
There's a little graphic thingy that says colors and apple and magenta. That's kind of blocking the way a little bit.
Okay. Thank you. I think it's this one here. Is it gone now?
Yes, it is good.
Okay, good. Thank you for pointing that out. Yeah, so what we need to do is, as I said, maybe I should actually correct this also right now to avoid a problem. Yep, so this state is occupied in the ground state, and you remove one, and this state is unoccupied in the ground state, and you create one. So end result is that you have moved one electron from here to over there, and that's how you can describe the excited state. But this is kind of inconvenient if you think about this, because when you actually excite a state, you have to remove a particle. So that is actually not a very simple description, because it's kind of counterintuitive. To excite a state, you have to remove a particle. But it turns out that there's an idea called hole. And you might have seen this idea in the context of condensed matter physics, where this is actually used a lot, but it's not restricted to this. I can tell an example in atomic physics and nuclear physics in a few moments, where the idea of hole is actually very useful. So here's a little trick you can do. Namely that if you actually define a new annihilation operator of momentum P, which is nothing but the creation operator at momentum minus P, and it sounds very strange, but just bear with me. And this is a creation operator of a hole at momentum P, which is nothing but the annihilation operator of the particle at momentum minus P. So just regard this as a pure mathematical trick for the moment, and then look at the canonical anti-commutation relations among them. So if you look at the dp d dagger q anti-commutation relation from this definition, d of p is b dagger of minus p. D dagger q is b of minus q. So this is b dagger minus p this is B minus Q, and their anti-commutator is Kronecker delta of minus P comma minus Q, so which is the same thing as Kronecker delta of P and Q. So minus P and minus Q are the same when P and Q are the same. So it turns out that this definition of new creation and annihilation operators satisfy the canonical anti-commutation relations. So if you actually define it this way, this ground state we talked about, where all states are occupied up to this Fermi momentum, can be described in a way which is more familiar to us, namely that this ground state is annihilated by the annihilation operator of all the momenta above Fermi momentum because it's unoccupied. So if you try to annihilate this, you cannot do so, so that returns 0. But all the states up to the Fermi momentum PF, these states are already occupied by particles, which means that if you try to raise it by B dagger, then that returns 0. But we just defined that this B dagger to be D of a whole, namely that this is the annihilation operator of the whole. So then the ground state looks like this is actually a vacuum state of particles and holes. So particles can be created above the Fermi momentum. Holes can be created below the Fermi momentum. And for the annihilation operators for either particle and hole, then annihilation operators annihilate the ground state of the system. So this is now the new vacuum state for both annihilation operators, which turns out to be the same thing as the original ground state described using particles alone. So this was just a mathematical trick, but this actually seems to help us in understanding the ground state now being the vacuum state, but referring not just the particle vacuum state, but also the whole vacuum state. So the D of P is the annihilation operator whole, which is the same thing as creating a particle here. D dagger of Q is the creation operator of the whole, which is the same thing as removing particle. And if you do it this way, this BP of 1 is now rewritten as D dagger of P of 0, namely that this is actually a creation of a whole and particle in pairs. So exciting the system by moving one electron below the Fermi surface and moving it above the Fermi surface is now understood as a creation of a whole and particle. It's a pair creation. And that's the way you can now describe the excitation to the system. So now the ground state is the vacuum state with respect to both particles and holes create annihilation operator. And excited state is described using creation operator, which is actually mathematically sort of easier to deal with, because when you create something, it kind of makes sense that you raise the energy to the excited state. But because the whole is referring to the absence of the particle, whole has an opposite electric charge, opposite momentum, and opposite energy. So opposite charge means that if you are talking about the whole of an electron, that's an absence of the negative charge of the electron. So the whole has a positive charge. And also it's obvious the momentum is reversed because when I define D of P, this is B dagger of minus P. Namely that if you create a particle of momentum minus P, that's the same thing as removing a whole of momentum P. If you remove the particle with momentum minus P, that's the same thing as creating a whole of the momentum P. So that's something which is important, namely that when you define this idea of a whole, being creating a whole here, you're removing the charge of the electron that's negative. So that's the same thing as adding a positive charge. And we are removing the electron of momentum P, that's the same thing as adding momentum minus P. Again, I see a typo here. Let me correct this for now, right away. Okay, so removing an electron out of this Fermi degenerate C is the same thing as creating a whole of particle, whole of momentum minus P, because the whole system now loses the momentum p, which is the same thing as adding the momentum minus p. So that's the idea of a hole. And that actually turns out to be very useful when you think about atoms and nuclei. So let me, I'll come back to that examples in a moment. So let me stop here, and I'm sure you got some questions here. No questions?
I have a question.
Right.
So in your last bullet point, it says a hole has opposite energy, but since energy goes with p squared, wouldn't a hole have the same energy as the particle?
That's right. Yeah, exactly.
Okay, so it's just opposite. Okay.
Mm-hmm.
Yeah.
Mm-hmm.
Just yeah.
Thank you for asking the question. Any other questions here?
Can you explain again why the vacuums are equal?
You mean this line here?
Yeah.
Yeah. So the ground state used to be that when you try to add more particle, namely b dagger of p, on the occupied state 1, that vanishes. And now we relabeled b dagger by d. So we're looking for a state where you cannot remove a hole. Namely that in the point of view of the hole, that's the state that's annihilated by the annihilation operator. And that's what we normally call 0. So what used to be the state 1 has now become state 0 when you switch to the language of the hole from the particle. So what used to be the state that is already occupied, that's 1, is a state that is now unoccupied by a hole. So that you can create a hole, which is the same thing as you can remove a particle. So the role of the vacuum state 0 and the occupied state 1 had been switched when you go to particles to holes. Does that answer your question, Emily?
Yeah, I think so.
Okay, good.
Yeah.
Any
thanks.
other questions here? Okay, so if you've seen an explicit example, the next slide, I hope that would make actually better sense. So we all know that the noble gas like argon has a closed shell. So in the case of argon, the 1s states are fully occupied by 2 electrons. 2s and 2p states are all occupied. 3s and 3p states are all occupied. So that's the noble gas. So it's the closed shell atom. When you actually take 1 electron away, so that the outermost shell, the 3p shell, is not fully occupied, but it's missing 1 particle. That's the case of the chlorine atom, so one of the halogen atoms. And so rather than talking about putting 5 electrons into 3p orbitals, which can accommodate 6 electrons, then you have to actually combine all of these 5 electrons to write down the multi-particle wave function to deal with it. But now that the argon atom is known to be closed shell, it's much easier to regard the chlorine atom to be missing an electron away from argon, which is the same thing as adding a hole to this closed shell atom, namely argon. So we now regard this argon configuration to be some kind of the ground state. And the chlorine atom can be described as adding a hole to that ground state. Then you're talking about a single particle problem instead of a 5 electron problem, or if we add all of them together, the 15, how many are they? 17 electron problem, which is obviously very complicated. But now you switched from the 17 electron problem to 1 hole problem. And this hole is obtained by removing one of the electrons. So the hole now carries a positive charge. And then creating a hole is a very simple description of what's going on here. In particular, when you ask the question, what is the angular momentum of the chlorine atom? You don't need to add angular momenta of 17 electrons to work out its wave function, add all the angular momenta and so on, but rather only talking about adding a hole into this 3p orbital. So you know right away that the orbital angular momentum of this chlorine atom is 1. Without doing any calculation, without doing any additional angular momenta, without dealing with the Krebs-Gordon coefficients, you know ahead of the time that this is the angular momentum 1. So to work out the quantum numbers and various physical observables, if you have this closed shell kind of configuration, removing particles is a lot easier than keep adding particles. So that's the idea of a hole. So when you actually talk about even the total angular momentum, trying to add both spin and orbital angular momentum, you can talk about now a hole in 3p states. And you have to figure out just one particle problem, but adding a single spin and single orbital angular momentum. And so in the case of this 3p orbital, clearly the orbital angular momentum is 1. Spin of electron is always 1/2. You have two possibilities. So 1 and 1/2 would add up to total angular momentum 1/2 or 3/2. And which one is the ground state is the question you can ask. And then, of course, that depends on the spin-orbit coupling. And in the case of just adding 1 electron to the 3p orbital, we know that would actually give you the lower energy state with anti-parallel orbital and the spin angular momentum. So that's J equal 1/2. That's a sign of the coupling electron to the spin-orbit coupling from the Coulomb potential. So that's spin 1/2. On the other hand, when you're looking at the hole, then you're talking about adding a positive charge object with the spin-orbit coupling. And then the spin-orbit coupling originally comes from the Coulomb potential. So adding a positive charge will give you the opposite sign for the spin-orbit coupling. And that's how you can actually get the J equals 3/2 state being the ground state. And if you want to work that out from the original language, again, you have to add all these electrons together with the spin-orbit coupling to different J states. And you keep adding the 10 electrons, 6 electrons in the p orbitals. And in the case of chlorine, you're missing 1, so they have to add 5 electrons. Yeah, that's right, 5 was right. So 5 electrons into the 3p orbital together with the spin-orbit coupling, and you figure out what the angular momentum of the ground state would be. But if you switch to this language of Hall, you can pretend this is the single particle problem. The only thing you need to be careful about it is that the charge is now positive instead of negative. And then you know which combination of spin and orbital angular momentum would give you the ground state. So using the idea of a hole can make the problem a lot simpler. And when you look at the also semiconductors in condensed matter systems, then you are removing 1 electron in what is called a p-type semiconductor by doping semiconductor with an element which is a one atomic number fewer than the semiconductor using. And so if you do that, that defines a p-type semiconductor, which actually removes 1 electron. So we normally actually describe this by adding a hole instead of removing an electron. Then you are talking about the charge carrier in the semiconductor to be positively charged because you're looking at the holes. And you can look at the band spectrum of the holes moving in certain relationship between the energy and momentum. And so that's the way it's much easier to describe the property of a semiconductor, again, using holes instead of particles. And finally, when you go to relativistic quantum field theory, which we will do in a few weeks, then you can have a system where you have an electron, relativistic electron, but you can create a hole of the electron, and that actually turns out to be antimatter positron. So it turns out that in relativistic quantum field theory, you find electron states with a negative energy, but you also find a solution which have negative energies. And for negative energy states, just like in the case of the metal, you have to all occupy these negative energy states to find the ground state. Because the chemical potential is 0, everything below 0 have to be occupied. Then you can remove one of the states with negative energy, and that is an absence of electron with negative energy, which is the same thing as creating a hole of positive energy, and the hole now carries a positive charge, and that actually turns out to be the idea of an antimatter, namely the positron. So we will come back and talk about this later. This is just a preview of it. But what I'm telling you here is that this idea of a hole is very useful, ranging from condensed matter systems, atomic systems, and even relativistic quantum field theory. And the hole always carries the opposite electric charge from the particle. And then you can always create a pair of a particle and a hole by conserving electric charges. And this pair creation of particle and hole, in a case of relativistic quantum field theory, turns out to be a pair creation of matter particles and antimatter particles. So if you send a powerful electron, a photon, a gamma ray photon with high energy, enough high energies, you can create matter particle and antimatter particle at the same time, which is the pair creation of matter and antimatter. And so that is described by using this idea of a hole. So the hole in a previous slide looks like just a mathematical trick of replacing the creation operator of an occupied state by an annihilation operator of the occupied state by creation operator, just because that seems to satisfy the same anti-commutation relations. So that was a mathematical trick. But this actually turns out to be extremely useful because in some cases, you can replace this horrible multi-particle system into just a single particle problem, which is a lot easier to deal with. You can talk about the pair creation of particle and a hole. And in the relativistic case, that description turns out to be really fundamentally important because that turns out to be really the idea of the antimatter in the universe. And so that's how the idea of hole is actually very useful across the board in many different systems. And so that's the usefulness of this description of an occupied state of a particle versus the vacant state of a hole. And then you can add holes to the system to work out various physical observables much easier compared to the idea of dealing with whole number of electrons in the system. Okay, so let me stop here again. I'm sure you have questions. Now that you have, we are looking at explicit problem, I hope that would give you better intuition and also more questions.
Yeah, I have a question.
Go ahead, Daniel.
Okay, so you said like a photon, which has like positive energy, can somehow like interact with something and then create a negative energy hole in which a positron appears. How exactly does that happen? How does a photon like interact with this negative energy?
Right. So if you think of the atomic system, that's easier to understand. If you send a photon here, then you can excite this electron to now 4s orbital, let's say. Then you have created a vacancy in 3p, that's a hole, and you created an electron, now occupancy in the higher energy orbital 4s. Now using this idea of a hole, that's the same thing as creating a hole in 3p state orbital and creating a particle in 4s orbital, and that's a pair creation of a particle and a hole. So in the same way, for this relativistic QFT, you send in a photon would knock out this electron in negative energy state, would bring it to the positive energy state. So you are moving electron from negative energy state to positive energy state. But now using this language of the hole, you have created an electron of obviously positive energy, and now you created a hole of absence of negative energy. It's the same thing as positive energy creation. So that's the creation of the matter electron and antimatter positron in a pair. Does that make sense?
So a follow-up question to that would be, so I guess I'm hearing it works for like high energies. Could a similar argument, like if you had popped in instead of from 1s to 2s, like would you still observe an antiparticle?
So if you start with, let's say, helium, then you have only 1s orbitals occupied. And if you send in a photon, you can excite 1s electron to 2s electron. Then you have one electron in 2s, one vacancy in 1s, that's the hole. And that's the same thing as pair creation of a hole in 1s orbital and the particle in 2s orbital. Am I answering your question, Daniel?
A little bit, because it's like a particle, not like some sort of like idea, like, oh, because it seems like we started off with like an idea, like, oh, this hole is just kind of like representing like a vacancy in a negative charge, but now we're kind of saying, oh, that's a physical thing, and we're going to call it a positron.
That's right.
Like, how do you know the difference between the two?
Well, so there's no difference because, as you saw in the previous slide, they are just mathematically equivalent. So for the particles, they satisfy the usual canonical anti-commutation relations. If you switch to the language of the hole, they also satisfy the usual canonical anti-commutation relations. You just need to switch around what do you mean by the ground state of the system. So the ground state used to be an occupied state of the particle, but now the ground state used to be the vacuum state of a hole. So you just switch your language from particle to hole, and mathematically they are just totally equivalent. So it's just a matter of convenience. If you would like to talk about absence of the particle or presence of the hole, you just choose whichever is more convenient for you. So that's the idea of the hole. So mathematically, either one is just good enough. But one of them is more useful than the other one because it can be simpler. And then you choose the language as a whole. Instead, if you're looking at, for example, what is the next thing is argon? Is this not is it sodium? No. I forgot. Does any of you remember what comes after argon?
Potassium.
Oh, the potassium. Okay. Is it? All right. So then potassium is actually adding one electron in the next orbital. Then you're talking about presence of a single electron in addition to the closed shell. So in that case, you'd rather treat it as a problem of a single electron and add it to the closed shell the atom, which doesn't have any orbital or spin or any other quantum numbers. So then you can treat it as if you're talking about a single particle problem. On the other hand, in the case of chlorine, you are removing one particle from argon, then you are talking about a single hole problem. And that's a much easier way of talking about it instead of talking about 5 electrons in the p orbitals. So depending on the problem, using the language of the particle is easier in the case of potassium, or using the language of hole is easier in the case of the chlorine. And you just choose whichever is easier for the problem at hand. I don't know if that satisfies Daniel, does it?
Yeah, I guess we can treat it as like you were saying, a kind of a matter of convenience.
Yes.
I can see it that way.
Okay, good. Any other questions here?
I have a question.
Mm-hmm.
What's the difference between treating adding a hole and then looking at chlorine versus an argon ion? Because I feel like if you're just adding a hole, you should be talking about an argon ion, not a chlorine atom with an extra proton and neutron or whatever.
Yeah, that's a very good question. So I sort of glossed that over. Obviously, when talking about the chlorine atom, you have a different nucleus from argon nucleus. So what I have to then do is to look at the chlorine nucleus first, but you add one too many electrons so that you have how many? It's 18 electrons now. And adding 18 electrons, I can fully occupy all of the shells. So now I have a closed shell atom. And for the purpose of working out the quantum numbers of atomic states, closed shell has no quantum numbers. All the angular momentum cancels. So that's an easy system to deal with. So instead of talking about the chlorine atom with 17 electrons, I would rather talk about chlorine atom first with the 18 electrons all occupying to create a closed shell atom, and then remove one electron afterwards. And then it becomes a problem of having one hole in addition to the closed shell, and treat the problem as if it is a single particle problem rather than 17 electron problem. Does that answer your question, Adi?
Yeah, thank you.
Okay, good. Any further questions?
Yeah, I had a question.
Go ahead.
I was wondering, so is it possible for like electron pairs to create like some type of fake bosonic state. So like, could you have like, I guess like triplet state of like electrons, like form a Bose-Einstein condensate, where you have like just a bunch of
That's an
pairs?
excellent question. We will be coming to that later when we start talking about the helium-3 superfluid. So you are anticipating what's coming next. So thank you for that. But we'll get there. So not now. Thank you, Cameron.
Okay.
Any other questions? Okay, so I talked about how useful the idea of hole may be in the case of semiconductor, case of multi-electron atoms, relativistic QFT. Now I'd like to go to the nuclear physics, which is probably new to you. But even in nuclear physics, there is a concept of shell. And there's something called the nuclear shell model. That doesn't work for every nuclei, it turns out. So it's actually less rigorous, less useful theory compared to atomic shells. Nuclear physics is a very complicated physics. All the particles in the nucleus, namely protons and neutrons, interact very strongly compared to electron that interacts with the Coulomb potential, which is a weak interaction because that is subject to the fine structure constant of 1 part in 137. So you're talking about weak coupling because fine structure constant is small. In the case of the nuclear physics, that corresponds to fine structure constant is actually very large, something like 15. So it's definitely not a weakly coupled system. It's very strongly coupled. It's very difficult to understand theoretically, but it turns out that there is similar idea to the closed shell, which turns out to be very useful. So you start with the idea of just a simple harmonic oscillator. And as you see, physicists always start with the harmonic oscillators because this is something we know and we can solve. So just pretend that the nucleus is same thing as putting neutrons and protons into this harmonic oscillator potential as the 0th order approximation. But this is the 3-dimensional harmonic oscillator. So when you actually work out the energy levels, then you have to think about 3-dimensional harmonic oscillator. But then you flatten out the long-range portion of the potential because we know you can knock out protons and neutrons out of a nucleus. So the potential energy cannot keep rising, then you can never escape, but should flatten out so that you can take a proton out of this potential. So starting from this harmonic oscillator potential, what you have to do is flatten out the long-range portion of the potential. And then what you know is that higher angular momentum states, higher orbital angular momentum states would decrease their energies. Because if you look at the same harmonic oscillator potential of, let's say, 1 to 3rd excited, starting from 0, you excited twice, then you have the energy of 2 h bar omega added to the ground state. And that state can be classified as a state with the 0 orbital angular momentum, namely S state, and also a state with the 2 unit of orbital angular momentum, namely D states. And as you know, these states have the wave functions more spread out to outside compared to S states. So if you flatten out the potential on this outer portion, then the d orbital state would experience this decrease in potential much more than the S states. And as a result, these states would go down more than S states. And in addition, you add the spin orbit coupling, which you would actually prefer in the case of the nuclear physics, the higher total angular momentum J compared to the lower angular momentum J. And so you see the split of a state with given P, given L, into two states with different J values. And you always find the higher J states to go down more than lower J states. So that's the idea of the nuclear shell model. So you first start with a harmonic oscillator as a 0th order approximation. You flatten out the outer portion of the potential as the next order approximation. Then you put in the spin orbit coupling to the second level of approximation. And that actually turns out to give you already a very good description of various states inside the nuclei. And then, just like in the case of atomic physics, if you have a large gap between states that are occupied and states that are not occupied, you find a particularly stable configuration of the protons and neutrons in this potential. So that's the analogous thing to the closed shell atoms, like the noble gas. And then you find a particular stability of those configurations. And then you talk about magic numbers, namely these numbers, 2, 8, 20, 28, 50, 82, 126 are called magic numbers, because if you have a nucleus with protons, with let's say 8 protons, and also neutrons, 8 of them, then that would add up to 16. 8 protons correspond to oxygen. So then you're talking about oxygen 16 nucleus. And in that case, both proton has the magic number. Neutron also has a magic number. Then you say that's a doubly magic nucleus. And it turns out the oxygen 16 nucleus is particularly stable. So this is the schematics I mentioned already on the previous slide. We start with a harmonic oscillator. You have a ground state. You add 1 h bar omega. You add 2 h bar omega, and so on and so forth. So these are the harmonic oscillator states. And because this is a spherically symmetric 3-dimensional harmonic oscillator, then you have creation operator for each direction, x, y, and z. So going from the ground state to the first excited state, you have the possibility of adding 3 different creation operators. So you have 3 states. And that's the same thing as having actually p orbital, because L equal 1 corresponds to 2L plus 1, 3 states. And so that's how you can see that this first excited state is a p orbital. So they are called 1p states, which is a different terminology from atomic physics, where the excited states in p orbital are 2s instead of 1p, 2p instead of 1p. But that's what nuclear physicists decided to do. So going from 1s to the first excited state is called 1p. If you add additional creation operator, now you have 3 creation operators, and you can use 2 of them. So that will give you 6 combinations. You can choose the same creation operator twice. That gives you 3 possibilities. Or you can choose 2 different creation operators. And then you have the number of 3 choose 2, that's 3. So altogether you have 6 possibilities. So you have 6 states in the doubly excited state with the energy 2h bar omega. And those 6 states would fall into 1s state. So that's called 2s, because you already have 1s. The second one's called 2s. And you have remaining 5 states, and they neatly find themselves in a d orbital, because d means L equal 2. 2L plus 1 is 5. So altogether, you have 6 states. So in this way, you can all classify all these harmonic oscillator states into the orbital angular momenta. So the lowest state is S. The first excited state is P. Second excited state is S and D. Third excited state is P and F. Fourth excited state turns out to be S and D and G. G is L equal to 4. Fifth excited state turns out to be P, F, and H. H is the orbital angular momentum 7, and so on and so forth. So that's how you understand these states in terms of the orbital angular momentum. And then when you flatten out this outer portion of the potential, I told you the states with larger orbital angular momenta would go down. So that's what you see here. So 2h bar omega, the doubly excited harmonic oscillator, had both S and D states, but these states with higher orbital momenta will go down relative to 2s. 3h bar omega states in harmonic oscillator had both p and f orbitals. F orbital has a higher orbital angular momenta, so that would go down relative to 2p. So each of these angular momentum states now split in terms of their orbital angular momenta, and you always see the highest orbital angular momentum states to be the lowest within those shells. Now I see chats. I froze. Did I freeze? Apparently not for everybody.
For a
Am
minute.
I doing okay?
Yeah.
Okay, thank you. So that's the idea of the schematics here. And then if you look at, for example, this 1D state that has orbital angular momentum 2, but both protons and neutrons have spin 1/2. So you're adding 2 to 1/2. You have two possibilities. The 2 plus 1/2 is 5/2. 2 minus 1/2 is 3/2. So this d orbital would now split to two j values of j equal 5/2 and j equal 3/2. And this is the opposite from the case of the spin-orbit coupling in the atoms. In nucleus, spin-orbit coupling prefers larger j compared to smaller j. So d 5/2 would go down, d 3/2 would go up. As a result, they're split. And the 2s state, which uniquely points to j equal 1/2 now, would sit somewhere in between. So that's the way all of these states would end up splitting like this. And finally, you look at the positions where you seem to see the widest gaps among the different energy levels. So if you occupy both of these 1s states with two different spins, so j is 1/2, there are two states, that's one closed shell, and that's a magic number 2. When you fully occupy these 1p states, then you occupy 3 orbital angular momentum states with 2 spins, so you have 6 states. You add 6 more, that's 8. That's yet another closed shell magic number 8. And same here, if you fully occupy all of these, the second excited states of the harmonic oscillator, that gives you total number of 20. That's a magic number 20. But next one is a little bit weird because this F7 states come down so much. One, due to flattening out the potential at the outer portion of the space. So F has pretty big angular momentum, 3, so it comes down quite a bit. In addition, spin-orbit coupling is also pretty large, so that comes down also even further. So that ends up developing a gap between this F7 states to the rest of its partners in this third excited state of the harmonic oscillator. So these 8 states within F7 will come down with a pretty big gap here. So that gives you a new magic number of 28. And after this gap, you occupy the rest of the third excited states. But next level at the 4h bar omega, g orbital would come down also so much that this actually gets bunched together with the rest of 3h bar omega states. And that gives you the next magic number of 50, and so on and so forth. And of course, which one comes down so far to create a big gap, and which one gets bunched together with the lower one is a quantitative question. You need to get some idea on how big the effect of this lowering down the potential at the outer portion is, how big the spin-orbit coupling is. So this is sort of empirical. It's no fundamental theory for this, unfortunately, in this very complicated nuclear physics. But experimentally, this idea would explain these magic numbers as observed by data when you see very stable nuclei, such as these doubly magic nuclei. Helium-4 uses magic number 2 for both protons and neutrons, hence the total mass number is 4. Oxygen-16, already mentioned, 8 plus 8 is 16. Calcium-40 is 20 plus 20, that's 40. If you use also this magic number 28 for neutrons, but 20 for protons, same atomic number, that's still calcium, but now mass number is 48. And calcium-48 is also a doubly magic nucleus. If you use 28 for the proton, and also 28, and also 20 for the neutron, the total number is 48, that's nickel 48. If you use 28 for both protons and neutrons, that's a nickel 56. If you use 28 protons and 50 neutrons, that's a nickel 78. And all these are doubly magic nuclei, and so on and so forth. And largest doubly magic nucleus we know is lead 208. And so that's the way you can understand why these particular nuclei are especially stable. Painfully chemistry flashbacks. I'm sorry, Natalie. But anyway, so this is the way you can understand why certain nuclei are particularly stable. And once you know that these are particularly stable nuclei, you can start thinking about, for example, oxygen-17. as if it was single particle problem of single neutron in the potential. But at the same time, you can understand oxygen 15 by removing one neutron, and you can understand the property of oxygen 15 as a whole of a neutron. Then you can immediately understand its quantum numbers. Adding one neutron to oxygen 16 would put one neutron in this 1d 5/2 orbital. So you know the ground state of oxygen 17 is 5/2 spin. And d orbital with L equal 2 has the parity even. The parity goes like -1 to the L. L equal 2 gives you positive parity, so that's plus. So again, without doing any calculations, just by looking at this energy level diagram, you know oxygen 17 nucleus has a ground state of 5/2 plus. On the other hand, when you're talking about oxygen 15, you are creating a hole in this lower orbital 1p 1/2. So that's basically the anti-neutron or hole in neutron in 1p 1/2 orbital. So you know the ground state is 1/2 in terms of total angular momentum. P orbital has L equal 1, -1 to the L is -1, that's the odd parity. So the parity of this oxygen 15 nucleus has to be negative. And that's one hole in 1p 1/2 orbital. So again, you know the quantum number of oxygen 15 without doing any calculation of adding up angular momentum of 15 nucleons. You treat it as if it was single particle problem, single hole of the neutron in doubly magic nucleus oxygen 16, and that's how you can figure the quantum number of this nucleus without doing any calculations whatsoever. So this is another example where idea of hole is actually very useful. Okay, let me stop here. Let me go back one slide where I was explaining this nuclear shell model. And let me go from there if you have any questions about it. Questions? Oops. So the idea that you start with the harmonic oscillator potential as a zeroth order approximation, you flatten out the outer portion of potential that would bring down energy levels over higher orbital angular momenta. And then for a given high orbital angular momentum, you split them into two different J states, L plus 1/2 and L plus minus 1/2 states. And in nuclear shell model, you accept this idea that L plus 1/2 states come down, L minus 1/2 states would go up by the spin orbit coupling. And once you accept all these three things, then you can understand the presence of these magic numbers. And that was the success of the nuclear shell model. And as you see here, Maria Geppert-Meyer actually received the Nobel Prize together with Hans Jensen on the invention of this nuclear shell model back in 60s. Any questions about this? I haven't actually looked at no, go ahead.
Are the doubly magic atoms, are they more or less stable than the noble gases?
So this is actually talking about the nuclei. So for the noble gases, you're talking about the closed shell atoms with electrons occupying up to certain states fully with a wide gap above it. Here we're talking about the states of the nucleus. And in the nuclear potential, you're putting protons and neutrons into this potential, this empirical shell model potential, and find the states where you have a wide gap between the occupied states and the unoccupied states. And that is the magic number nuclei. So we are talking about two different things here. Noble gas is about electron states, and shell model is about the nucleon. Nucleon is the generic name referring to both protons and neutrons. We're talking about the states of the nucleons in this nuclear shell model.
Okay, right. So
Is
this is
that
like
clear,
a strong, yeah, so this is like a strong weak force potential, and the other one was a Coulomb potential.
That's right, yeah.
Okay.
Any other questions here?
But
I bet this is the first time
also-
you see nuclear physics. Natalie?
Yes, to that. And also, but also there's a Coulomb potential between the protons as well.
Excellent. Yeah, that's an excellent point. Yes. So the protons would repel each other. So you're putting a bunch of protons into this potential well, but you also need to include the impact of Coulomb repulsions among them.
Yes.
And it turns out that Coulomb repulsion is smaller, weaker compared to this binding effect from this nuclear force. So you can treat the Coulomb potential as a perturbation to the system. The first thing you consider is this nuclear shell model. You occupy states with the protons and neutrons, and you put in the Coulomb potential as an afterthought. But that's of course important too, especially when you go to atoms with a large number of protons, namely large atomic number. And that's the reason why if you go to a larger and larger nuclei, you need to put in more neutrons compared to protons to keep the nucleus bound. So for smaller doubly magic nuclei, you basically have the same number of protons and neutrons. So for small nuclei, that's sort of the norm. The stable nuclei tend to have equal number of protons and neutrons, both of them occupying the magic number is a particularly stable nuclei. But as you keep going to higher atomic numbers, for example, in the case of nickel, I meant actually like a lead. So lead-208 is the sum of two magic numbers, and I need to be sure. So 82 protons and 126 neutrons. So to create a stable lead nucleus, you are putting in far more neutrons compared to protons. Because putting more proton, of course, occupies a nuclear shell state, but receives much bigger repulsion from the Coulomb interaction. So energetically, it's much more favorable to put more neutrons into the nucleus compared to putting more protons into the nucleus. So you end up with much larger number of neutrons compared to protons. So that's how you have this lead-208 as a very stable nucleus with a big disparity between number of protons and neutrons. And that's again the rule of thumb. For bigger nuclei, you have fewer protons, more neutrons to create a stable nucleus, precisely because of this Coulomb repulsion you pointed out, Natalie. And so you put in as an afterthought, but nonetheless, you have to consider it. And there's something called the island of stability in nuclei. What configuration of number of protons and neutrons are stable? So you start with the 45 degrees diagonal for the smaller nuclei. But if you go to larger nuclei, then it starts to bend towards larger number of neutrons. And that's because of this Coulomb repulsion among the protons. So that's a very important question, Natalie. And does that make sense?
Yeah, it does.
Okay, great, thank you.
Thanks.
Any other questions here? As I said, this is probably the first time you see anything about nuclear physics, so I'm sure you have more questions. Don't be shy. No? And one of the things you learned in, for example, freshman physics class, I believe, is that there is something called alpha decay of nuclei, right? And alpha decay would basically spit out alpha particle, which is made of 2 protons and 2 neutrons, which is the same thing as helium-4 nucleus. So the reason why alpha particle can come out from nuclei in nuclear alpha decays is that helium-4 is particularly stable configuration. So if you have unstable nucleus and you would like to settle down to a low energy state by spitting out something, but spitting out something is always trying to minimize energy. So you would like to spit out something that is already very low energy configuration, namely very low energy state. And helium-4 is a particularly tightly bound nucleus. And that's why helium-4 is the combination that will come out. And hence the nuclear alpha decay. So I believe you got told that nucleus can undergo 3 types of decays, and gamma decay is emitting a photon, which is de-excitation of the nucleus, where, for example, 1 proton in a high orbital will come down to lower orbital, just like in the atomic system. That's the gamma decay. Alpha decay is you have some complex nucleus, which is kind of shaky and unstable, but by spitting out this particularly tightly bound configuration of helium-4, you can settle down to lower energy state, and that's the idea of alpha decay. And beta decay is different. One of the neutrons inside the nucleus would decay into proton by emitting an electron and anti-neutrino. That has to do with the weak interaction, not electromagnetism or strong interaction. That's something totally different. So in nuclear decays, you see all three forces we know in nature: electromagnetism in gamma decay, strong interaction in alpha decay, and weak interaction in beta decay. And so that's something you learn, I believe, in freshman physics, modern physics class. But now you understand why these three decays are what would come out in nuclear physics, understanding this nuclear shell model. So gamma decay is just de-excitation like in the atom system by emitting a photon. And the alpha decay is spitting out this particularly tightly bound configuration of helium-4. Okay, that's I think that's something useful to know. Any further questions about this nuclear shell model? Okay, so this is meant to be yet another example where talking about a hole is a very good way of describing certain configurations close to magic numbers. But if you're missing a few particles, dealing with holes is far easier than dealing with particles. And so this is oxygen case is just meant to be an example of that idea. But anyway, so this was meant to sort of double up on an introduction to nuclear physics, which doesn't appear in most textbooks these days. But also the idea of using holes is a useful description of simple systems. And so this was meant to be a demonstration of the two different ideas. But I hope that makes sense. And I think this is also useful to know. And I did make a remark that shell model is not always useful. And that's because if you are sort of halfway in between these stable magic numbers, sometimes you find the nucleus not round, but shaped like a cigar. And then this spherically symmetric potential is not a useful starting point. And they are called deformed nuclei. And it turns out that these deformed nuclei are far more stable compared to spherical nuclei if you're sort of halfway between these magic numbers. And that's when this simple idea of nuclear shell model is not very useful. So that's why I mentioned ahead of the time that this is not always useful. Shell model is pretty useful when you're looking at small nuclei or somewhere close to the magic numbers. But if you're far away from magic numbers, it may not be useful. That's why the applicability is far more limited in nuclear shell model compared to atomic physics. So that's just a warning. So this doesn't work for every nucleus, unfortunately, but for some large set of nuclei, this is still a very useful description and hence worthy of Nobel Prize. Okay, any other questions here? Okay, so this is something this was known already from the 60s, I mentioned. I was very surprised. Actually, this decade, there was a new discovery of new magic number. And this is an experiment called the radioactive isotope beam facility in Riken, Japan. This is a particle accelerator where you can accelerate radioactive ions inside the accelerator. And they're, of course, radioactive, hence they decay. So they're limited lifetime. So you have to accelerate them quickly so that you can circulate them in the machine like this one. And they claim to have discovered the new magic number 34. And this is a paper published in Nature. And I copied their energy level diagram. And this is what they found. So in the case of this nuclear shell model, I mentioned already that different orbital states would sort of go down. And then you have further splitting of the spin orbit coupling. And in the diagram I showed earlier, this F5 halves was lower than P1 half. And let me go back and show it. So where is it? Yeah, that's right. This 1 F5 halves was lower than 2 P1 half. But this is actually a combination of spin orbit coupling raising 1 F5 halves, but this flattening potential lowering F states with the P states. So there's a competition going on. So depending on the size of the spin orbit coupling, you may have a situation that this 1 F5 halves would go above 2 P1 half. And that's indeed apparently that's happening here. And maybe I misspoke, sorry. The comparison is, yeah, that's right. So this F5 half states is typically below P1 half for the iron and chromium nuclei. But for some atoms, their ordering may switch And you may develop even a fairly big gap between phi half states, which is now above p 1/2 states. Then you have a magic number of 34. And that's apparently what they discovered. And calcium-34 is also a radioactive, namely they decay. So there's no natural abundance of them. You have to make them with accelerators. But once they make them by bombarding a certain nucleus on another nucleus, they created this calcium-54, which has the 34 the neutrons in addition to 20 protons. And they found a very stable configuration of the nuclei. So magic number is still useful, but which one gives you a magic number depends on this competition between flattening out of the higher L orbitals and spin orbit coupling. So it's a little subtle, and sometimes you see a new magic number actually created in this nuclear shell model. And that's actually a discovery in the 2013 or something. So this kind of nuclear physics is still ongoing, and we are learning new things in this area too. Okay, this is just to give you some progress that is happening in this field, still in this the ancient idea of the nuclear shell model. Okay, any questions about this? Okay, all right. So now comes the helium-3. So when you think about helium-3 instead of helium-4, we learned that helium-4 would become a superfluid at a very low temperature, and that's because of bosons and condensate. Helium-3, that is lacking one neutron. So we just learned that helium-4 nucleus is doubly magic nucleus. So helium is, in some sense, triply stable. You have closed shell of 2 electrons in one nest state. So closed shell for electron, and 2 protons in 1s1/2 nuclear shell state, 2 neutrons in 1s1/2 in nuclear shell state. It's a doubly magic nucleus. So it's closed shell for electrons, closed shell for neutrons, closed shell for protons. So helium turns out to be a very, very stable boson as a whole. Helium-3 is lacking one neutron out of this closed shell nucleus. And therefore, it's the same thing as adding one neutron hole to the closed shell. So this is a neutron hole in 1s1/2 orbital. So we know right away that helium-3 nucleus is spin 1/2. In its S state, so 1/2 plus even parity. So knowing this language of the nuclear shell model in a whole, we again know that helium-3 has a ground state of 1/2 plus. And helium-3 atom then has 2 electrons circling around this helium-3 nucleus. So as a whole, the 2 electrons in one s orbital, again, is a closed shell, no quantum number. So the only quantum number helium-3 has is spin 1/2 from this missing hole of the neutron in the nucleus. So overall, the whole thing is spin 1/2. So now you know how to figure out these quantum numbers, knowing the language of the whole. In spin 1/2 configuration with 3 nucleons and 2 electrons, as a whole is a fermion. So helium-3 as a whole is a fermion with spin 1/2. Now that we know this is the fermion, we can ask the question, what happens to the helium when you actually cool it down? So here, I'm just writing down what I already mentioned. Helium-3 nucleus is doubly magic plus neutron hole, and hence 1s1/2. Helium-3 atom is a closed shell 1s squared configuration, no additional quantum number, and hence the whole thing is spin 1/2 and fermion. Now, what happens when you cool the system? And you expect some kinds of Bose-Einstein condensate when you cool the system, but this is a fermion. So fermion cannot condense because you cannot occupy the 0 momentum state with the macroscopic number of fermions. But as the cameraman was already asking a few minutes earlier, if you think of pair of helium-3, pair of 2 spin 1/2 objects can form together to, for example, spin 0 configuration by spin up down. And that's actually a antisymmetric configuration. It turns out that it actually prefers the p wave configuration. I will talk about that in a moment. So it's not the spin one half spin. This antiparallel configuration is a preferred state, it turns out. But nonetheless, you can form an antisymmetric combination of two helium-3 atoms. Then the pair of two helium-3 atoms becomes a boson effectively. And you can talk about the condensate of that boson of two helium-3 atoms. And then you can talk about superfluid because of that. So when you put together two helium-3 atoms, you have a choice of putting two helium-3 atoms in even orbital angular momentum. And then the orbital part of the angular momentum is symmetric. You have to make sure it's a fermion. So the spin part of the wave function has to be antisymmetric, which corresponds to total spin 0. That's one possibility. Or you can have odd orbital angular momentum. Then orbital part of the angular momentum is antisymmetric. Then you have to use symmetric combination of spin wave functions. That's spin 1 as a whole. It turns out that in the case of helium-3, you have weak attractive force at long distances. But when they come very close to each other, they actually repel. There's a repulsive core. So they don't want to come too close to each other. In L equals 0 state, they would really overlap on top of each other. That doesn't turn out to be the lowest energy configuration. They would like to be a little bit away from each other. So it turns out that L equal 1 turns out to be the preferred configuration to lower the energy. And therefore, you have L equal 1, that's P wave. But we learned that odd L would require S equal 1. So that's spin 1 configuration. Then you add orbital angular momentum 1 to total spin 1. And then you have 9 possibilities here. 2L plus 1 is 3. 2S plus 1 is 3. Then you have 3 times 3, 9 possible configurations. So it turns out that you can describe a pair of helium-3 using the Schrödinger field with 9 components as a 3x3 matrix. So that sounds a little bit more complicated than what we used to do with the Bose-Einstein condensate of helium-4. The field, Schrödinger field, was just single helium-4. It's not a pair. And there was only one component because helium-4 is closed-shelled in everything. There's no angular momentum degree of freedom. There's no multiplicity. So single Schrödinger field was a good description to begin with. But in the case of helium-3, first of all, you have to consider a pair so that you can talk about its Bose-Einstein condensate. And pair of 3 helium-3 atoms turns out to be 9 possible configuration. So you arrange Schrödinger field in 3x3 matrix. So that sounds a lot more complicated. But at the end of the day, what you do is the same thing. So the Schrödinger field that describes this pair of the helium-3 now has an expectation value as a condensate. And that would lead to a superfluid. And I will show you the phase diagram on the next slide. But let me stop here. Are there any questions about this discussion here?
What would the components of this matrix be? Would that just be like the label of like L and S together?
That's right, right. So the
Okay.
L equal 1 means LZ can be 1, 0, minus 1. S equal 1 also means SZ can be 1, 0, minus 1. So out of this 3x3 matrix, you'll find LZ1 SZ1, LZ1 SZ0, LZ1 SZ minus 1. And now you go down in LZ, LZ0 SZ1, LZ0 SZ0, LZ0 SZ minus 1, and LZ minus 1 SZ1, LZ minus 1 SZ0, LZ minus 1 SZ minus 1. So that's the 9 configuration. And they arrange into this 3x3 matrix field. So this side is L, this side is S. Does that answer your question, Cameron?
Yeah, it does. Would this also possess like rotational invariance? Like if I were to, I guess
Yeah,
like with
so-
the matrix, like could you transform it?
That's exactly right. When you do spatial rotation, then L would rotate by 3x3 matrix. And S equal 1 also rotate as a 3x3 matrix. So this 3x3 matrix gets transformed by acting 3x3 rotation from the left for L, 3x3 rotation of S from the right. Does
great.
that make sense, Cameron? Okay.
Yeah,
Good.
that makes perfect sense. Thank you.
Any other questions about this?
I have a question.
Go ahead.
What differentiates a boson pair of helium-3 atoms and then just having two fermions, two separate helium-3 atoms? Like, what does it mean to have a pair?
Yeah, so you have one helium-3 atom, and you have yet another helium-3 atom. They weakly attract with each other, so they form, in some sense, a kind of bound state. And that bound state overall is a boson, and we describe this bound state as a boson in terms of the Schrödinger field. And this is the point where you might find it confusing, because we are talking about the Schrödinger field to describe a composite state. But none of you complained when we talked about helium-4 described by the Schrödinger field. Helium-4 is also a composite object made of 2 electrons, 2 protons, and 2 neutrons. As a whole, it's a spin-zero boson, and we actually use Schrödinger field to describe this helium-4 as a whole, as a single object. So now we are doing the same thing here. Now 2 helium-3 atoms, which is more complicated than helium-4. You have 2 electrons from one helium-3, 2 electrons from other helium-3. You have 2 protons, 1 neutron, but the whole thing is a boson with 1 orbital angular momentum and 1 unit of spin. Therefore, you have 9 states of this whole configuration. And we are describing this whole configuration using a single Schrödinger field with 9 components. So we're actually doing the same idea like what we used to do with the helium-4 superfluid. Now that we're talking about 2 atoms together, it might look bizarre that we are using this single field to describe this pair, but we have done that before in the case of helium-4. I didn't point that out to avoid possible confusion back then, but now we are actually sort of bringing out this possible confusion outright, and that might be indeed confusing. But we have actually used this idea successfully before. So it turns out that field theory is very versatile. Single field can refer to an elementary particle like an electron, but can also refer to composite objects like a helium-4, or even a pair of helium-3 atoms. And this whole thing can be described by a single quantum field, it turns out. And then we have a boson field, and therefore we can talk about Bose-Einstein condensate of that. So that's the argument how we'd like to describe the helium-3 superfluid. Does that answer your question, Adi?
Yes, thanks.
Good. Any other questions here? Okay, so it turns out that you can have a Bose-Einstein condensate of this. So in the case of helium-4, we describe the field for each helium-4 atom. And then you talked about the coherent state of that the creation operator for the helium-4 atoms. And that's how we end up describing the Bose-Einstein condensate. What we are talking about here is what is called the BCS state. BCS stands for Bodin, Cooper, and Schrieffer, who came up with a theory of the superconductivity. So in that case, you're talking about a pair of electrons, not helium-3. But helium-3 is also the same idea. It's a BCS state. It turns out that the BCS state is a funny linear combination of unoccupied state, the vacuum state, together with state with the pair of a helium-3 occupied. And pair is supposed to have 0 momentum, just like in the case of the Bose-Einstein condensate. So what that means, they have to pair up helium-3 atom with momentum P, another helium-3 atom with momentum minus P, and as a pair, it doesn't have any momentum. And you actually put this condensate of this pair state for all the different momentum states. So here I'm writing it only for single momentum mode, and I also create this linear combination for B dagger Q, B dagger minus Q for different momentum mode, and so on and so forth. So BCS state is a complicated complicated state as a whole, because you create this pair and take a linear superposition of unoccupied and occupied states. And once again, this is something you can do in QFT, because single Hilbert space has states with different number of particles in it, which is not possible in quantum mechanics. because the wave function has fixed number of arguments in it. And that's something we have used already for the coherent state for BEC. This is a linear superposition of states with many different number of particles. And here we are doing this now for fermions by creating a pair of fermions instead of a multiple bosons. But you create a pair for all kinds of different momentum configurations. So an end result is, again, you have a macroscopic number of pairs condensed in this superposition. And it turns out that this pair of fermions can be written in terms of Bogoliubov transformation again. So the idea is that you have this usual harmonic oscillator like a Hamiltonian, but you have two-body interaction with the attractive force among all of these creation-annihilation operators. And to minimize the energy in the spirit of variational method, you use this kind of BCS state. And because the BCS state is a linear combination of unoccupied state and W occupied state, BCS state has an expectation value of two annihilation operators. And usual vacuum state we talked about with the positive chemical potential was the step function. That was the case of the usual metal we talked about before. But when you take this linear superposition with unoccupied and W occupied state, you are sort of smearing around this Fermi energy. So these states are only partially occupied. These states are only partially vacant. So you are smearing around these Fermi energies. And that turns out to be the low energy state if you actually work out the variational principle. So attractive force among the fermions would actually prefer this BCS state over the step function state of the Fermi liquid. And that creates this complicated phase diagram because now the what condenses is the pair of fermions. I told you that pair of helium-3 atoms come in 9 possible configurations. So which component end up having this condensate would give you different phases of the superfluid, hence superfluid phase B and superfluid phase A. And this phase diagram is known experimentally, but it was the Anthony Leggett from the University of Illinois Urbana-Champaign who figured out this theory, and he got Nobel Prize for this, which is actually not a long time ago, maybe around the turn of the century. So the idea of the helium-3 superfluid is far more complicated because we have to deal with this finite orbital angular momentum, finite spin. But the idea is that the pair of fermions would condense. Then out of this Hamiltonian, then BB combination might have expectation value in the ground state. And if you replace this BB portion by the expectation value, you have a Hamiltonian that has B dagger, B dagger in it. B dagger, B dagger also has an expectation value in this BCS state. So if you replace B dagger by its expectation value in the ground state, you have a piece that is BB inside the Hamiltonian. And that's what you have seen before in Bose-Einstein condensate too. So if you ask the question, what is the excited state above the superfluid state? And you worked out this Bogoliubov spectrum. And to work out Bogoliubov spectrum, you had a Hamiltonian of B dagger B, and also B dagger B dagger, and BB inside this Hamiltonian. And you took funny linear combination of creation-annihilation operator to find the spectrum of excitation. And we do the same thing here. Namely that Bogoliubov transformation to diagonalize the Hamiltonian of this form, B dagger, and BB, in addition to B dagger B, you look at the size of this condensate of this BB operator, and that actually turns into this just delta. So this B dagger, BB interaction would be now replaced and simplified into two-body operator with B dagger and BB in it. And you try to diagonalize this. It turns out that if you take a linear combination of creation-annihilation operator, not with Koch and Cinch, like in the case of bosons, but in terms of cosine and sine for the fermion, you can maintain this canonical anti-commutation relation. CC anti-commute, CC dagger is 1, thanks to the properties of the sine and cosine functions, then your ground state is defined by a state annihilated by the annihilation operator C. And that actually turns out to be precisely the combination we talked about on the previous slide, which is a linear combination of vacuum state 0 and B dagger state. And you can verify that this state satisfies this definition of the ground state. You can also choose either in such a way that Hamiltonian becomes diagonal in C dagger and C. You don't have C dagger term, C term at all. Your Hamiltonian is now diagonalized in terms of C dagger C alone. And that's how you can understand why this linear combination is indeed the ground state of the system, which is the BCS state. BCS state does give you expectation value of this BB operator. Hence, you replace part of the Hamiltonian by this condensate. And that condensate precisely gives you the right ground state. So that's how everything works out self-consistently at the end of the day. So this is the idea called the BCS theory of fermion pair condensates. And the helium-3 superfluid is indeed described by this BCS state of the condensate of pair of fermions. So pair effectively behaves as a boson as a whole. Then you have a condensate of that boson combination of B minus BBP. And indeed, this BCS state is a condensate of that pair of the P and minus P states of fermions. And that's the idea of the BCS theory. Okay, so I ran out of time. So let me stop here and see if there are any questions.
I have a question.
Go ahead.
From the previous slide.
Okay.
Yeah. So when we considered the BEC, we considered that it was a condensate of all the bosons in the P equals 0 state.
That's right.
Right. But for the BCS and for the condensate of the fermion pairs, each pair is a boson, right?
Right.
And they each but each pair has to occupy a different momentum state.
That's right. Because
So
the fermion cannot occupy more than once in a given P state. If you have this boson with P and minus P together, let's say it has a condensate, but I can put more of these into the same P. So I instead use another B dagger with a different momentum and put that in there. Yet another B dagger with different momentum, create a condensate in it. Then I can have a macroscopic number of pairs condensing without conflicting with the Fermi statistics. And that's how we can get a macroscopic condensate in the BCS state.
Okay, so it doesn't have to be that they're all in the same state for it to be a condensate. They can. That's right. The pairs can be in different. Okay. States. Okay.
Actually, they have to be in different P.
Yeah.
In order to satisfy the Fermi statistics. So I'm writing this simply for one single momentum mode, but you have to take this linear combination for every P, and take a big tensor product among them all to get the full BCS state.
Cool. Thank you.
Thank you for asking the question, Wadi, to clarify it. Any other questions on this slide? No further question? And also on this? Everything okay? All right, so then we finish up the class. And as I said, the midterm exam will be posted later today. And I also have the office hour from 5 o'clock if you have any questions to ask, either about the current homework problem or what I covered in the class today. All right, have a good weekend.
Thanks, Professor.